Hey guys, this is Megan from OnlineMathCircle on the AIME video tutorials, and today we're going to look at 2009 AIME 1 problem number 15. In triangle ABC, AB equals 10, BC equals 14, and CA equals 16. Let D be a point in the interior of segment BC. Let IB and IC denote the incenters of triangles ABD and ACD respectively. The circumcircles of triangles BIBD and CICD meet at distinct points P and D. The maximum possible area of triangle BPC can be expressed in the form A minus B root C, where A, B, and C are positive integers, and C is not divisible by the square of any prime. Find A plus B plus C. So first of all, let's look at triangle ABC. We know here that AB equals 10, BC equals 14, and CA equals 16. And we want to try to find the measure of angle BAC so that we can work with the remaining angles in this figure. So we can use the law of cosines, and by doing so we have BC squared equals AB squared plus AC squared minus 2 times AB times AC times cosine of angle BAC. And substituting the given values, we have 14 squared, or 196, equal to AB squared, which is 100, plus AC squared, which is 256, minus 2 times 10 times 16 times cosine of angle BAC. And simplifying the right-hand side, we get 356 minus 320 times cosine of angle BAC. And so cosine of angle BAC is 356 minus 196 all over 320, which simplifies to 160 over 320, or 1/2. And so BAC is 60 degrees. Now, next thing we notice about the angles in this figure is that angle BO1D is equal to the sum of angle BO1IB and DO1IB, just by looking at this figure. Similarly, for angle CO2D, that is equal to the sum of angle CO2IC plus DO2IC. Now, looking closely at angles BO1IB and DO1IB, we see that these are central angles that intercept arcs BIB and DIB. And if we're looking at those arcs, we're looking at the minor arcs, right here and here. We see that the inscribed angle BDIB, which is this angle here, intercepts arc BIB, which is the same as the central angle of BO1IB. So that means the measure of angle IBDB is equal to 1/2 of angle BO1IB. And the measure of angle IBBD is equal to 1/2 of the measure of angle the measure of angle DO1IB. Similarly, if we look at this part of the figure here, we see that the inscribed angle ICCD is equal to 1/2 of is equal to 1/2 of DO2IC, and then the inscribed angle ICDC is equal to 1/2 of CO2IC. So we can make the following substitutions in these two equations, and then we get the measure of angle BO1D equal to that would be equal to 2 times measure of IBDB plus IBBD, and CO2D would be equal to 2 times the quantity of the sum of the angles DO2IC plus CO2IC. No, excuse me. That would be, sorry for the typo. That would be ICCD plus the angle measure of ICDC. Now, looking at these angles here, we see that the measures of IBBD and IBDB are 1/2 of the measures of angles ABD and ADB respectively. And the reason for this is because all the segments from the incenter of a triangle to the vertices of the triangle are serving as the angle bisectors of all the angles in the triangle. So that means the sum of these two angles here would be the same thing as ABD plus the measure of ADB. And similarly, right here, this will be the sum of ADC plus ACD.